Hello everyone. In this video we're going to be talking about ordinary differential equations, specifically solving ordinary differential equations with linear coefficients using the Laplace transformation. Okay. In this type of questions we're going to be giving initial boundary conditions. So we have y of 0 being equal to 1 and then y prime of 0 being equal to 1. Okay, so we have two conditions. Normally when the order is 2, you're going to be given two conditions so that you use them later on. Okay, so how do we do this? So firstly, we're going to be taking the Laplace transformation for both sides. So the left side becomes Laplace of y double prime plus y, and the right side becomes Laplace of 0. Okay, we know that Laplace transformation is a linear transformation, so basically this distributes over the two terms. So this becomes the Laplace of y double prime plus the Laplace of y, and the Laplace of 0 we can immediately say it's 0. Okay, so here for this term we're gonna be needing a rule. Okay, so the rule, it's something of this, like it look like this. The Laplace of nth derivative of y, this is gonna become s to the power of n. Okay, the Laplace of y, and then the power is gonna drop down, so it's a minus s n minus 1. So you see we get one less. Okay, and then this becomes what? This becomes y to the n minus 1 of 0, and this continues, so every term it decreases by 1 until you get lastly y at 0. Yeah, from right side, of course, this is a limit, we don't care about that right now. And then s here is to the power of 0 or just s. It's gonna be more clear once we use it here. Okay, so this becomes what? According to the rule, n here is 2 because the highest power here of derivative is 2. Okay, so the order is 2. So we're gonna have s to the power of 2. Okay, and then we're gonna be having Laplace of y, so s to the power of 2, just Laplace of y. Great. Then minus, so s, the power of s is gonna be 1 less, so basically just s. Yes, all right. And then this is going to be n minus 1, so the n minus 1 derivative of y, so 1 less derivative, so just y prime of 0. And then minus one more term, here you're gonna have s to the power of 0 or just 1, so you can just write 1, okay, or nothing. And then this is y prime of 0, so this one is y of 0. Okay, so this all came from this one. Okay, so it became 3 terms, and then you write this again, so this is a separate term. Okay, so plus, I'm gonna put it in a brackets, right? So plus Laplace of y, this is all equal to 0. Okay, so first things first, we have in two terms that include, let's say, y at the value of 0. Okay, so these two are given. We can see that y at 0 is 1, so we can write 1 here instead of this. And then y prime of 0 is 1, so also we can write 1 instead of this also. So the whole thing becomes s to the power of 2 Laplace of y. Okay, so minus s and then minus 1. Okay, also plus the Laplace of y equal to 0. Okay, so I'm gonna actually write it here. Okay, so from here I see Laplace of y is a common thing between these two terms. So if I factorize Laplace of y, what do I get? I'm gonna get s squared and plus y, 1, because I don't have anything next to it, so basically 1. And then this minus s, and then this minus 1, I'm going to move them both to the right side. So the whole thing becomes this s plus 1, okay? And what are we looking for here? We're looking for the original function here, so y. So we're going to be needing Laplace of y alone at the left side. So from here, Laplace of y is equal to, we can divide both sides by this s squared plus 1, s squared plus 1, okay? So these two cancel. So we're going to be having Laplace of y alone being equal to s plus 1 over s squared plus 1, okay? So from here, our thought procedure should be, well, what function is similar, let's say the Laplace of which function is similar to this? Well, personally, I don't know anything that the rule says this is the Laplace of that, for example, exponential function or sine or cosine. But I can do something simple here. I see this is a common denominator for these two terms. Why not distribute? So let's just do that. So this becomes what? S over s squared plus 1, and then 1. Okay, then 1 over s squared plus 1. So now I actually can recognize these two. So these two are both the Laplace of sine and cosine. Okay, so right here we have Laplace of y being equal to this. So if we take the, let's say, inverse Laplace transformation of this, okay? So we're taking the operator inverse Laplace for both sides. So in the inverse Laplace for s over s squared plus 1 plus the Laplace inverse of 1 over s squared plus 1, okay? So we recognize actually this one. This is, I think, it's cosine of x. And then the other one is sine of x. And we applied inverse Laplace to Laplace. So basically these two cancel because they are inverse operators. So from here, we can say y is equal to cosine of x plus sine of x. And this is actually